about sort of like let's say uh, um, basic and fundamental properties of a Luxolitnic semigroup, or the so-called optimal control formula. These are the same depending on different contexts. Okay. All right, so I guess that we can start slowly now. As you are aware that we are still on the way of proving the Wickham theorem. Is taking us a while to get there. Again, I'm doing it in a quite slowly and, but fundamental moves. Every lecture contains certain important information that I want to sort of explain it in detail to you. Um, and in order to prove the Wickham theorem, so earlier we already talked about, the existence of dominated functions, or, sub-solutions in the almost everywhere sense. That was fine. In order to prove the existence of such a solution that has the, backward characteristic property, um, we would need to discuss in depth about, the sort of like the backward characteristics and understand that deeply. And in doing so, we introduce the object ht of xy. um, that's essentially represents what I'm highlighting here on the left panel, represents for the minimal cost function going from x to y in the time t. Again, this is for the purpose of, doing the Wickham theorem. And one of the, most fundamental property that we have been able to shown was that, this is the key point, is that ht, mapping from Tn cross Tn to R, is uniformly Lipschitz for all t greater than equals to any fixed constant sigma greater than 0. So we would need to have a lower bound here, and if we have a lower bound for all such t greater than sigma, then we have that is uniformly Lipschitz, and we can say that the Lipschitz constant of ht dot dot is less than equal to c sigma for all t greater than equal to sigma greater than 0. Okay, so this is extremely important because it shows us that we have global property for all such t, even if t goes to infinity. And later on, we're going to be benefited a lot from this uniform Lipschitz estimate. And this is, in fact, a really important property of PDE, uniform estimates independent of the parameters. Okay, and by the end of last lecture, I already introduced to you certain, first instances of the Luxolitnic semigroup. I'm gonna do it more systematically today, and together with all such, proofs that I didn't do last time. So I'm redrawing this picture all the times. I explained it last time already from the optimization or optimal control viewpoint. I'm not gonna recall it too much, but I'm gonna just write that. So optimal control viewpoint. So the other day I was calling it U and UXT, and today I'm changing a little bit. It's still the same notion. I'm just changing it so that I'm fitting with Fatty's notion in the text. So we are given initial data. So the data given here is some function U that is a continuous function in the torus. So this is a space. Okay, space variable. Okay, so that's what given to us, and this is t is the time. We are standing at a point xt here. So this is a point xt in space and time. and we are trying to find all possible way to go from xt back to the time zero. You know, so you can go in various different ways, going like this along the curve eta, or going like along the curve gamma, or going, you know, along other curves, or going in a straight line, doesn't matter, all possible curves available to us. Okay, so if we go along the curve gamma, so I would have gamma mapping from 0t to with gamma t equals to x. And typically I would say that gamma 0 equals to y, doesn't matter. And the optimal control framework is that if you run, you know, along that part, you know, you can imagine that you are driving along the part, or, you know, you're controlling your boat or whatever along that part. And there, you know, the cost function consists of two parts. The first part is the so-called running cost. It's essentially, you know, the amount of gasoline, amount of whatever energy that we have to pay when we run along that part, which is integral from 0 to t L of gamma s, gamma dot of sds. And so it's more complicated than a normal calculus of variation problem, right? Because we would have also that the not just the running cost, it's exactly the calculus of variation problem, but we also have the terminal cost. So terminal cost, that is, if we reach the point here, which is, you know, like y equals to gamma 0, then we would have to pay something along, you know, along the terminal, right? And you, the given data represents for the terminal cost we have to pay. So it's u of gamma 0, which is u of y. I mean, because we let gamma 0 equals y. So then the point is that, so last time I defined it to be uxt, so we can still define so, but I'm respecting the notes in Fatih's book. So we define uh, that t minus is because, you know, going backward, so, you know, right, going from xt backward, so minus represent for that backward ux, I'm sorry, not xt, is equals to the minimizing problem. So minimize over all possible scenario, so all gamma in absolutely continuous 0t to the torus with endpoint gamma t equals to x of the sum of the two costs, right? Two costs, the running cost and the terminal cost. Okay? Again, it's going backward in time. That's why we say that it's sort of like whatever tt minus. And okay, you see that this can be rewritten easily into the fact that I'm taking minimizing over all possible parts here with two endpoints, gamma t equals to x and gamma 0 something. And then later on, after that, I'm taking minimizing over the first part plus the terminal data, right? So you see that readily this equals to infimum over ht of gamma 0x, right? Because this is the minimal cost connecting gamma 0 to x, right? And then plus u of gamma 0. So that's readily available to us because that's exactly the function ht defined, right? You can recall this is where ht is defined. That's exactly the, if you fix the two endpoints, that's exactly the minimal cost connecting them, right? And okay, so I have that equals to that. So you know, the second definition that you can also write is that then we can also write, we can also write that instead of writing the whole explicit optimal control formula, you can write this semi-group down like in a more implicit and simpler way of infimum over all y in the torus. So y here represents for gamma naught of ht of yx plus u of y. Okay. So what I'm thinking of here, I mean, this is same as the previous interpretation. What is a little bit different is that one thinking of here point xt. Right? Okay, and for any available y, of course, you can find many parts connecting y to x, right? But I'm taking already the minimum one. Maybe this is the minimum one. Not so precise, but maybe this is the minimum one. This one is the one that gives me the minimum cost connecting y to x, right? And then my problem is more complicated because it's coupled not just the minimum action on this ht functional, but once I can find a minimum part, then I'm adding also the terminal cost into account, and so I'm doing kind of like a double minimization problem, right? Okay. Any question for me here up to this point? Any question or concern? Okay, so that's good. And this is exactly the definition of the Luxolitnic semigroup. Okay. Maybe let me give you an example. Let's see. Maybe later. Okay. Yeah, because for that example, I would need to prove something. So to be done later, to be discussed, to be done later, is that we're gonna talk about an example on the Hoblox formula. Okay. So we're gonna talk about that. If you have taken PD1 in chapter 3, you have seen that. But I mean, we can interpret and do that rather quickly here. But okay, let's focus on the preliminary properties of the semigroup here and see how is everything going. All right. So I wrote down here the first two preliminary property. The first one is easy. Let me highlight it right away. It's just a upper bound and lower bound of the semigroup. What it's telling me is that, what we are considering is not something unbounded and something sort of going to infinity or stuff like that. That's easy. The second property is remarkable. I think we mentioned it a little bit last time, is that even though if you start with u, which is the initial data, is only a continuous function, but this semigroup property, semigroup has the regularizing property. What it does is that if you go up just a little bit in time, then it's automatically makes your function better. You go from a continuous function right away to a Lipschitz functions. And furthermore, if for all time t greater than sigma, then your semigroup is Lipschitz with constant at most c sigma. And you can see clearly here, to prove this property, we're going to use exactly. So I would say that the first one is quite straightforward. We're going to prove it anyway. Straightforward. Of the proposition. The second one is that we use readily or crucially the point that the function ht is Lipschitz, right? With Lip constant at most c sigma for t greater than or equals to sigma. Okay, so that's sort of the key point. I'm highlighting it right away. Okay, so let's do it. Well, the first one is clear. Let's just go through it line by line. you have, by definition, tt is the infimum here, right? Again, I mean, now I have two formulas. I'm just using whatever formula is more suitable for me. The first one is obvious. I'm just taking worst case scenario. The first, is minimum over all u, over all points of u. And then the action functional of L is always greater than or equal to T times the minimum of L. That's it, right? So that's that. Second point, let's see, is that we also write down the formula, right? Minimum of the ht function plus u of y. And okay, we can bound it also by worst case scenario because it's minimum over y. So I can take the point from here to here. I can take the point y to be z so that u z equals to min of u, right? So I let y to be that point. Then is less than equals to that particular the value of that particular z, right? And that gives me that minimum of in the torus, right? It's less than equals to minimum in the torus. And then the other term, I'm just bounding it by the worst case scenario, which is the maximum of the ht function. Okay. So again, it's just upper and lower bound. Simple, but it indeed shows that our object is finite. Okay. Now, the regularizing effect, and I'll mention it by the end, that we also have Hoblox formula, and that's some actually very important objects in the literature. Uh, uh, we get to that soon. But now let's just prove it. Okay, so let me write down here. So I mean, to prove two, right? It's like so fixed t greater than equals to sigma, and also x and z in the torus. We want to compare, like t minus of ux versus t minus of uz, right? Those are the two objects we would like to compare. This one with this one. And again, if we haven't done all the preparation steps earlier, it would be actually not easy to do so. But because we have done all such preparations, now I'm quite, comfortable with dealing with this, because I can just write out the formula, right? This is infimum is the mean. We talked about that already. So mean of y in the torus, ht of yx plus u of y, right? And h of the function is continuous in y. So I know that this is realized at some point. So this equals to ht of x bar x plus u of x bar for some x bar in the torus, right? Again, because h of the function is continuous in y, so the sum is a continuous function in y, so the minimum has to be realized at some points, say x bar. And by the way, this minimization problem also doesn't have a unique solution. So note that x bar might not be unique. For those of you who have done a problem concerning shocks formations, so if x bar is not unique, then that means that there are two characteristics that run into each other at xt. So that's where shock is formed for Hamilton-Jacobi, also conservation law. Okay. Whatever. So that's good. Yeah. So you see that I have come so far with the realization that tt minus of ux is equals to this value, right? And on the other hand, you can see right away that, this term on the right here, tt minus of uz, this one, because of the minimization problem, is always less than equals to a particular value I plug in, right? And I'm plugging in exactly the value ht of x bar z plus u of x bar, right? So what I'm doing is that, like on one hand, I have tt minus of ux equals to the one that I just circled on the right panel. On the other hand, I have that tt minus of uz is less than equals to this one. I'm purposely plugging in the same x bar so that I can eliminate the u of x bar, right? Because u is only continuous, so I don't want to deal with its regularity. HT is having better regularity, so I'm using it. It's just a very sort of simple idea, but everything is simple so far in this class. We are just building upon things that are simple. So then I have tt minus of ux minus tt minus of uz is going to be less than equals to ht of x bar x plus ux bar minus ht x bar z plus ux bar, right? And the ux bar goes away. So this is less than equals to ht of x bar x minus ht of x bar z, right? And now I'm using exactly the thing I mentioned, that the Lipschitz property of ht, because t is greater or equals to sigma, right? So this is going to be less than equals to c sigma of x minus z, okay? Then by symmetric argument, gives eventually that I can compare tt minus of ux minus tt minus of uz is less than equals to c sigma x minus z for t greater equals to sigma. Okay, so rather simple but quite remarkable, again. So this is the so-called regularizing effect. So this is so regularizing effect of tt minus. Okay. And this regularizing effect is actually very important, in analysis, even from baby routine time, and a sort of a very effective way to do regularization was by doing convolution with a standard kernel. We have used it quite sometimes, and this is a new kind of regularizing effect by using PDE or semi-group property. Okay. Any questions or concerns? Okay, good. So now let's prove the three more, I wouldn't say advanced, but more like what I mean, three further properties of the semi-group. Okay, and then I'll come back to the example that I promised you guys from the beginning. Okay, so the first one I'm highlighting here is depending on the context. So this is the so-called semi-group property. Okay, the term that I'm highlighting here, that if you plus a constant, then the constant can be pulled out. That's simple. That's obvious. But this property is called semi-group property. Semi-group property, or also it's called dynamic programming principle. I mentioned last time. And again, for any problem in dynamics or in PDE, semigroup property is extremely important. What it tells us is that, okay, you start with any given initial data, let's say you want to go up to time, let's say you want to go up to time t plus t prime, right? So you can decide to go, straight forward. So I mean, in a way that you can go, straightly from here up to that point. So if you go straightly, you have is t of t plus t prime of u, okay? But on the other hand, you can decide to go, like instead of going directly to the time of t plus t prime, you go, two steps, right? You go from time 0 first to time t, okay? And then from time t, you go to t plus t prime, right? So if you decided to go to do so, then so if you go straight from 0 to t plus t prime, you get t prime of u. But you can do it intermediately, so going from 0 to t and t to t plus t prime, right? So going from 0 to t, it gives you from here to here, you have it's going from u to t of u, right? And then you take t of u as the initial data, you go from t to t plus t prime, so that means that you go for another amount of t prime. So going from here to here, that kind of gives you t. So sometimes I would forget the minus because it's quite a lot of signs here. So forgive me if I'm forgetting those. Okay? So you can decide to go in two consecutive steps, and that's give you that. So the semi-group property of dynamic programming principle tells you that it doesn't matter. They commute, right? You can go either ways. So that's that. We sort of proved it last time. I recall it. It's rather quick. Okay. Then we also have an important property called the monotone property. So if you start with u less than equals to v, then the semi-group property, the semi-group respects that, and this is important in certain geometric problems and also in certain PD problems that have the maximum principle. It tells you that things are ordered, right? You go with u less than v, then when the semi-group goes ahead, then TTU is still less than equal to TTV. So I'm omitting the minus here because it's too much of words to say, okay. And finally, this is remarkable, but it's also not very surprising. This is only correct for the first order equation. For second order equation, it's completely messed up. Is that if I have, U is the infimum of a family of solutions, then the semi-group of an infimum of this solution is going to be infimum of this semi-group. Okay. So this is very remarkable because it tells us that the inf operator can be inside or outside. Okay, but it's not too surprising because you see that already from our formula we have mean of a bunch of things and mean of mean commute, right? If I take min max, it's not equals to max min in general, but if I take min min, it's always equal to min min. It's okay to switch the order of a bunch of means. Okay. All right, so let's do this. Yeah, I mean, the first part we did it. I'm just recalling it here. You can recall to the last part of our lecture last time. But we can just write down. So it's infimum over y of uy plus ht plus t prime of yz, right? So first part here, we are just going to use the formula that h of t plus t prime of yz equals to infimum over intermediate value z in the torus, going from ht of y to z first, and then ht prime z to x. So that's the formula we are using, right? So that's exactly what we wrote here. The above equals to the next term in the next line, And then we are putting, again, because it's inf over y and inf over z, I'm pulling the inf out over all y and z. Okay, so I'm writing it's as three terms in the summation here. The next step is that I'm squeezing the inf over y in, right? You see, I'm interchanging the order of the inf here. This is not a problem because it's all the infs together, right? So putting the inf of the y in, I have this one, right? And then the other one, I still kept it the same. And by definition, the inf of the first one equals to tt minus of uz, right? And the second one is still being kept. And by definition, this is nothing but tt prime composed with tt of u, and that's it. So so we have that. The property of adding a constant is obvious because you just put a constant in and the constant can be in or out, right? You can just pull it out. Okay. The second property, it looks obvious, but this is actually an important property that tt minus is order preserving. Here, what I meant is that if you take u less than equals to v, then you would have tt minus of u is less than equals to tt minus of v. Again, this is a very important property of semi-group theory or of certain PDEs or geometric objects that have the maximum principle. For example, in an analog of this one in geometry. So an analog in geometric analysis is the motion by mean curvature. You take two possible you take two smooth manifold. So you start with gamma and close the other manifold like epsilon. Okay, so if gamma enclose epsilon and you let the two evolve with respect to the motion by mean curvature going inward, then what it tells you is still that you always have that the E of tau, the region E of tau, E of t enclosed is going to be always the subset of the region that gamma of t enclosed as time goes. So that the order preserving, right? You have the two manifolds moving inward, and if one is enclosed by the other, then that one is always being enclosed by the other, at this string. So that's sort of like the order preserving property. Okay. And you see the proof is obvious. It's obvious because you have, you write out the formula for tt of ux. You have that, and then you just replace u by v, right? Because u is less than or equal to v, and that's it. Okay. Again, but believe me, this is a very important property. And finally, let's prove the instability. It's exactly going along the line. I'm writing down there's the first infimum here over y. That infimum over y is being kept, and u of y is being replaced by infimum over a family of ui for I in I, right? And I pull the infimum out. I have that. And I switch the order of the inf, right? So I switch the order of the inf. So in all of this proof, a key point here is that infimum over a set A infimum over set B equals to infimum over set B infimum over set I. So, you know, that's the key point that allows us to switch the order of the inf. And again, this is also true for sup alone, but if you do inf sup and replace by sup inf, then we have to be careful. It's not always true if you switch those order. So I switch the order, and then, you know, by switching the order, then I have the inf of I in I is being kept outside here. Okay. And remark, in Fatty's book and other places, they can define the semi-group for, you know, you can even start with just a bounded function, or even a bounded from above or bounded from below functions. And after a while, it becomes also Lipschitz, but I'm avoiding those technicalities because they are not needed. I'm starting right away with continuous functions that are, you know, not too bad, right? Those are already nice objects to start with. Okay, so I owe you an example on the Luxolitnic Hoblox formula, but before that, let's pause and discussion. Let me pause here for questions or concerns or anything you want to discuss first. Oh yeah, I forgot to say one thing. By the way, in numerical analysis, you know, computing this semigroup, there are some methods to compute this. Still up to now, people are trying to do general computation for you know, like finding solutions to Hamilton-Jacobi equations, especially in the non-convex setting. Then it's really hard. In the convex setting, there are certain methods called semi-Lagrangian method that use exactly this semi-group property. So yeah, so I have some space here. So in terms of numerics, I'm not really deep into this, but I know a little bit about that numerics. So there's a so-called semi-Lagrangian method. Then, you know, computing this semi-group is a big deal. What people have been doing is that they are computing it for small time steps, of course. And you start with time step 0, and you go to time step tau and 2 tau, and so T1, T2, and so TK is K tau. So what people have been doing is that they try to compute up to the time step TK, then they use exactly the formula that you have. It's equals to mean or inf over OY of T minus of TK minus of U X plus HT is H tau of what I'm writing. Yes, that's hold on. It should be UI, sorry, minimum over Y, uy plus h tau of y going to x. So I mean, it's a very natural thing, right? You go from tk minus 1 to tk, you know, like going from y to some x here, trying to find what's going to be the best case scenario, and try to find minimization, try to solve this minimization problem, you know, step by step, iteratively. And along the way, they are writing down also the Euler-Lagrange equation, because h tau of yx is solving the minimization problem. It's quite complicated, but that's essentially the idea. The whole semi-Lagrangian method. This is a big business. I mean, especially the Italian group, and they use exactly this idea. Okay, it's not easy. Okay, any question or concerns? Okay, so let me do the Hoblox formula. So Hoblox formula corresponds to the case that H only depends on P. So H is only H of P. There's no spatial dependence, or you can say that it's homogeneous in X. And correspondingly, the Lagrangian is only L of V, only depending on velocity. And a particular example is that your H of P is 1/2 of P squared. Correspondingly, that L of V is 1/2 of V squared. Okay, so that's an example to keep in our mind. Then I want to talk to you about, then again, let me just rewrite the semi-group property. Tt minus of u of x is just the minimum of y, of u of y plus ht of yx. Okay, so in the case that L only depends on V, or H only depends on V, then this one can be simplified. So this one can be simplified. Okay, so let's do it. What is this ht of yx anyway? You have this is y, this is x. You try to reach from y to x, in an amount of time t, right? And in particular, when it's homogeneous in space, and this is exactly also the proof why the Euclidean distance is the smallest distance, why the straight line is the smallest one. I'm gonna prove it in a very sort of like twisted and modern language here, right? So I have ht of yx equals to the infimum over all curves that I have gamma 0 equals to y, gamma t equals to x of the action function, right? So integral from 0 to t of L of gamma dot of s ds. Again, there's no gamma s here, right? It's spatial independent. And now I'm not gonna use the Jensen inequality. Okay, so 1 over t integral from 0 to t L of gamma dot of s ds. So I'm taking 1 over t because that's the average of the integral, right? The integral has the length t, and taking 1 over t gives me the measure 1. This is greater than equals to L of integral from 0 to t 1 over t gamma dot of s ds. Okay, so this is exactly Jensen inequality. So this is actually the actual proof of why the in Euclidean geometry the straight line is of smallest distance. The rigorous proof, actually. Okay. And that's pretty much it. I'm estimating that for any curve going along from y to x, turns out that going in a straight line is of smallest cost, because the right hand side equals to L of what 1 over t times 1 over t times gamma t minus gamma 0, right? Gamma t is x, gamma 0 is y. So that's that. And this corresponds to exactly this curve that you can take, gamma bar of t to be nothing but y plus s times x minus y over t for 0 less than equals to s less than equal to t. That's exactly the minimizer. because L is uniformly convex. So this is the only the unique minimizer actually, right? So that's really beautiful. So it turns out that ht of yx is nothing but just going in a straight line, right? So it essentially maybe using a better different colors better here. It's exactly what t times L of x minus y over t, and minimizer is the straight line connecting from y to x. Okay. Right. So that's beautiful, and it gives us the so-called, this is exactly the Hoblox formula, the famous Hoblox formula for Hamilton-Jacobi equation. This was done in the 50s, 40s, and if you also use it for Burger's equation, it's a so-called Luxolitnic formula. That's why we have the name Luxolitnic semigroup. Uh, this is mean of y in the torus of u of y plus t times L of x minus y over t. Okay. And remark, in case that L of v equals to 1/2 v square, then we have the explicit formula that tt minus of ux equals to minimum of y in the torus of uy plus t times 1/2 times x minus y over t square. This can be written as minimum of y in the torus uy plus 1 over 2t times x minus y square. Okay. And in the literature, this is called, this formula in particular is a so-called Inf convolution of u. So you're given a function u that is merely continuous, and then you do Inf convolution. It's essentially you're solving a PD here, but you can just write out the formula. It's really interesting. You're taking minimum of u together with a quadratic function. Okay, so you're doing Inf convolution. So suddenly, from the function that is only continuous, you have that your function is Lipschitz, and in fact, this function is even better. Is give me 1 second. Is semi-concave in X. So whatever that is, it's a beautiful thing. It's a very important tool in various different areas that they use this new sort of convolution idea to go from a not so nice function. After you do convolution, you have a pretty nice function to deal with. And this idea is actually, for example, the key idea for Bob Jensen to prove results in infinity Laplacian, or also in second order Hamilton-Jacobi-Bauman equations to prove well-Posner's theory. And also use a lot in Caffarelli type results, when you need to do regularizations of various kind of PDEs. Okay, I guess that I'm stopping now. You guys have been a bit quiet today. Any points of discussions, anything you want to discuss about? Please do tell me.
I'm just curious, is it possible to define this operator in terms of a convolution, or is this just kind of an intuitive name for it because of its smoothing effect?
Yeah, so that's a very good question. So I mean, in general, people do say, even for the Hoblox formula, they say that this is also a Inf convolution type. So uh, uh, so what is great about this is that you have, not just your function is Lipschitz, but can be semi-concave or semi-convex. So you go from something that is merely continuous to something that's sort of like convex or concave type. So that's remarkable. Now for a more general form, like if you take ht of yx, you can still call this one convolutions, but that's you know uh, more abstract to be studied. But in fact, in the WCAM community, they also call this one like Inf convolution or subconvolution, and it being used sort of like correctly, it does gives you a lot more information. And it's just always the key points that this is sort of like a remarkable but important point that's different between sort of parabolic PD and wave PD. Is that for parabolic PD you start with something that is sort of fine, not too good, but if you run the flow, the solution becomes automatically much better, and that sort of smoothing effect is essentially because of this sort of phenomena. But for the wave equations, that it doesn't get better. It's just staying sort of barely like the initial data. So that's sort of the key point. But indeed, I mean, for the general object in WCAM theory, they also call it like Inf convolution and subconvolution. Uh, Historically, this is the formula I'm writing here is called Inf convolution. That's sort of from historical viewpoint standpoint. And uh, people have only figured this one out and used them since 1989 or something like that. So not too long ago. So it was a breakthrough that Bob Jensen used this sort of like idea to prove uh, well-postness for second order equations. Um, so that's really remarkable. Any other concerns? Yeah, so if not, then thank you all again. We are going gentle in a gentle way, but I like it because I can explain to you a lot about historical standpoints and also about the progress of the field. You can see that although they look pretty simple, but a lot of the progress were only done in the last 30 years. I mean, I'm saying that there are still a lot of room for deep and systematic developments, and it's not easy, but it's great. So other than that, then I'll see you again on Wednesday.
Oh, sorry. I actually have a question. Uh,
Yes.
so you say that, okay, so this doesn't hold true for second order equation, but is there similar formula with some like correction?
So the yes. So the problem for second order equation, that like there is certain, how should I put it? So the like the inf property for the last one here, it doesn't hold. The problem with that is essentially because of the fact that if it's a first order equation, technically you can switch the sign of the first order equation is still a first order equation. However, for second order equation, if you take the heat operator, for example, you put the minus sign to that, you have the wave operator. So you change completely the context of the problem. So that's why that to have this instability property, it just doesn't hold. And that's one of the key point why second order equation is much harder. For example, you can look into my book. There was some parts that was explaining that I forgot where is it, but maybe end of chapter 2 or something. So I mean, for it's very specific first order equations that this improperty is being preserved, and it's very nice for a lot of purposes. But without that property, that's one of the reasons why Bob Jensen had to use this Inf convolution to smooth up the solution a little bit to do the math. And also recently, as I mentioned, there was certain analog of optimal transport that I was trying to do with Diogo Gomez and Hiroyoshi Mitake. And we face some very crucial difficulties about this Inf property. And we could do something, but there are still a lot of hidden points that we still don't understand. So I mean, that's how I put it. So I would say, okay, so I would say that it's still open in the okay, in understanding deeply why it fails.
I see.
Yeah. So
Okay. Thank you.
yeah. So it's touching certain research problems already, and yeah. Yeah, the maybe the only point I can say is that if you put them, minus size to the heat equation to the heat operator, you're gonna end up with a wave operator, and that's exactly, it doesn't have a maximum principle there. But can we do something better than that? Then we could, but we are still far away from a much better understanding. Yeah. Okay, so great. Thanks a lot for your questions. Yeah, I always love to discuss stuff with you, and sometimes my discussions are not clear, probably because those are still research problems out there. Yeah, so let's resume on Wednesday. Thank you all, and stay safe and healthy as usual. See you later.